functions, and we're going to do some real world examples. All right, our first example that we're going to look with is to celebrate the new millennium. British Airways announced in 1996 it plans to fund construction of the world's largest Ferris wheel. The wheel was designed to measure approximately 500 feet in diameter. That's pretty important for what we need, and to carry up to 80 passengers and 32 capsules. There's some information we probably don't need for our problem. The wheel was designed to turn continuously and to be slow enough for people to hop on and off while it turns, completing a single rotation once every 20 minutes. So there we go. So here, down on the ground, suppose you board this Ferris wheel at ground level. Let time t, so our height would be equal to 0, and our t would be equal to 0. Okay? So t is going to represent the time since you boarded in minutes, and let h represent your height above the ground. Well, notice that along our diameters here, we know that these are 500 feet. All right? So what is half of 500? Yeah, half of 500 is 250. Okay? So that means that our h here is 250. Well, how much time would go by to reach 250 feet off the ground? Well, if it takes 20 to go all the way around, then that means we have 5 minutes. Okay? Once we're at the top, then we know that the h is 500. It has taken us half the time to reach the top. Okay? So we can keep filling this in down here. So we have 250, we have 500. As we come back down the downside, notice that t would be 15 minutes, and we would be back at 250 feet for our h. So notice how this has divided up. And then notice that the 20, we're also at 0. And then back at 25, we're moving for a second rotation. So we're at 250 feet. Then back down, back continuing up at 30, we reach 500. And then at 35, we're going back down towards the ground, so we're back at 250. Okay. So exactly what type of motion is happening here? Okay. Alrighty, this is a much nicer graph than the one I was looking at. And again, it is demonstrating your periodic motion. Notice that this one takes it a step further, that it divides your quadrants, cuts them in half again by 45 degrees. And so you can actually, figure out half the time between 0 and 5 is 2.5. And so you can figure out your half times as you go around. Technically, you could figure out your height, but that's a little above this. So again, we're looking at periodic motion as we go around, okay? So as we talked about earlier, we can see the pattern, okay? And we're going to take a look at now what happens if we plot these numbers, and instead of just going between 0 and 20, we go from 0 to 180, okay? So what are your observations? Okay. What would be a good description of the shape of the graph if the data points were connected with a smooth curve? Can you see any way that this would work? Okay, and what natural phenomena have this shape? So yes, you are correct, even though I'm going to have a hard time drawing it. This would be a sine or cosine wave. I mean, there isn't really any difference between a sine and cosine wave, except at the points where they start and stop, okay? So, and then what are our characteristics that we're going to be interested in? Okay. So again, since the Ferris wheel data is periodic, we can use a periodic function to model relationship between our height and time. And either the cosine function or the sine function will do. But we're going to have to learn a little more about the variations of these functions. And you were giving me some terminology that we might use, okay? So let's take a look at our definitions. Yeah, we're going to use the word period or wavelength if f is the length of one complete cycle. The midline. Midline is the horizontal line midway between the function's minimum and maximum values. The amplitude is the distance between the function's maximum or minimum value and the midline. The phase or horizontal shift, okay, this is the number of units from that the start of the cycle is away from being at the midline, and we'll take a more in-depth look at that. And here is where these definitions, these words show up. Notice that because we start at the midline here, they trace out in black. That would be a sine wave because it starts at the midline, it ends at the midline, okay? And so we can call this here like one period, um, which they emphasize then here. And each period, notice, is 20 minutes, okay? Our amplitude, if you take the minimum of 0, the maximum of 500, divide that by 2 is 250, and our midline also is at 250. Notice, though, that our, our phase shift is 5 minutes. Notice how it's negative, but that makes sense because the phase shift is to the right. And with it being to the right, we have a negative phase shift. Now, if it had been to the left, it would have been positive. And again, this goes back to your horizontal transformation. Okay, for now, let's simplify things and only consider the sine function. Similar relationships may be noticed in the cosine function, okay? And again, A is for our amplitude, B is our frequency, okay? Um, Keep in mind that B must be found by 2 pi and divided by your period, okay? Now the period is found by taking 2 pi and dividing by the frequency. And so it's often popular in these types of problems. You'll find the period and then have to find the frequency. And then H, your height, is the horizontal shift to the right if H is less than 0, horizontal shift to the left if H is greater than. Notice that it is divided by your frequency. And K is the vertical shift up or down. Okay? All right, we're going to take a look at this little graph right here. And we're going to find the equation for the graph of the sinusoidal function. And we're going to do this together, kind of step by step. And then you all are going to do 2 of these on your own with Ferris wheels, okay? We have to determine the amplitude of the function. Notice that our height here is at 5 and our minimum is at -3. So please tell me what the amplitude would be. That's right. We would have for the amplitude a 5 minus a -3, which means that we would have 8. Remember, these always are divided by 2. And so our amplitude is 4. What's our midline? This is kind of a cheat, but notice this line going through here is at 1, and so our midline is at 1. Now we have to determine the period. And the way that I determine the period is I looked at this point here at -3, and I traced out the wave until it hit the midline again at the correct spot of 17. So I literally would have 17 plus the 3 that's on the other side, and that's going to give me 20. So whatever these units are, my period is 20. Okay, and we can use this now to determine the value of B. Okay, so remember, that b is going to be equal to 2 pi divided by this 20, which means that my frequency is going to be pi over 10. All right. And then we do have a phase shift. Notice how our cosine wave is 2 off of where it should be, and it is moved to the right. Okay. And by the way, this should be a P for period. All right. So that's what we're looking at here. Let's continue on. Hang on, there was one really important message back here. When you try to set this up, make sure that your calculator modem is in radians. This was really important because I was checking out some of these equations and I couldn't get the calculator to graph correctly until I Googled it. And yeah, radians. You must be in radians to make your cosine and sine work properly. Okay, so here we have the amplitude being found, the midline being found, the period, which we read off the graph. Finding the frequency, we also found that pi over 10. Now here comes the kicker. How do we find the phase shift? And I told you that the phase shift was 2. So we're going to take that 2 and we are going to multiply it by the pi over 10. Okay, which will wind up simplifying down to pi over 5. So your equation would look like this. Y equals 4 cosine pi over 10x minus pi over 5 plus 1. Okay, let's come back to our Ferris wheel situation, okay? And upon reading the graph, we can see that the amplitude is 250. We have a period of 20, a midline value of 250, and we have a phase shift 5 minutes to the right. Okay, so in order to find our frequency, B is equal to 2 pi over the period, or 2 pi over 20, which is equal to pi over 10. We need to find the phase shift C, and that's 5 times pi over 10, which is equal to pi over 2, okay? And because it's to the right, it's negative. Thus, our equation would look like y equals 250, the sine of pi over 10x minus the pi over 2 plus the midline of 250. Heads up, the cosine equation is exactly the same as the sine equation, except what are we missing? That's right. We're actually missing the phase shift. There is no phase shift because your cosine starts right here at 0, 0. No phase shift. But notice that we do have a negative in front. And the reason why we have the negative in front of the cosine is because this graph starts at the minimum of the cosine. Okay, a regular cosine wave starts at the maximum. If you start at the minimum, you have to have a negative in front of it. All right, let us go ahead, and I actually have this and the next problem in a page, and you guys are going to go into breakout rooms, and you are going to work on these two Ferris wheel problems together, and then you're going to bring your answers back. Alrighty, it's good to see you back. Let's take a look at, see if you got the same answers as what we're supposed to get. So what was the minimum height? That's right, it was 0 meters. And at what time does the minimum occur? Okay, the minimum is going to occur at 0 and 20 minutes. And then what is our maximum height for this? The diameter was 100 meters, so that means our maximum is 100 meters. And at what time does the maximum occur? That's right, it occurs at 10 minutes. Then we can graph this out. And by putting the points down and then graphing the line, we can see again, we are actually looking at another cosine wave. I think I'd rather deal with the cosine wave and not have a phase shift. Okay, So we know the midline is 50 because it's 100 minus 0 divided by 2 is 50. Uh, and the amplitude is also 50. The period for one rotation is 20 minutes, so our frequency is pi over 10. The phase shift is 5 minutes to the right. That's if we were doing the sine wave, okay? So notice we have 5 minutes, that's a pi over 2. And then again, the cosine wave is negative because the cosine starts at the minimum, okay? It starts at the minimum. All right, here was the second Ferris wheel that you were supposed to work with, and this was definitely a little different. The Ferris wheel with a diameter of 122 meters rotates clockwise at a constant speed. The wheel completes 3 rotations every hour. The bottom of the Ferris wheel is 13 meters above the ground. So that means that each rotation is going to be so much. So in this case, instead of our maximum height and minimum height is 13 meters different, okay? Because your minimum is at 13, but notice that your maximum is going to be the 122 plus 13. And in fact, notice that the height over here, did you notice that it was 61, half of the diameter plus 13? So you have to take into account the minimum height of 13. And then again, if you're rotating 3 rotations every hour, 60 minutes divided by 3 gives you 20 minutes of rotation. Again, we can plot this out and you'll notice, again, that notice how we're not along the x-axis anymore, but we are 13 meters above the x-axis. So that has moved everything up. Okay. The amplitude was 61. The height off the ground is 13. So the midline changes to 74. One complete cycle was 60 minutes divided by 3 equals 20. The frequency, again, is 2 pi divided by 20. If you want this as a cosine, notice you have to have the negative because the cosine wave starts at the minimum. And the sine wave has a phase shift, though, and we can figure that out. And notice that, again, the sine has a phase shift of negative 2 pi over 2. Okay? Many natural phenomena display periodic behavior similar to the up and down motion of a Ferris wheel set. Please name a few of these either in the chat or go ahead and unmute yourself. Okay, some examples that I've come up with, which you might have mentioned: back and forth motion of a pendulum or swing, up and down motion of a weight bouncing on a spring, hours of daylight, believe it or not, each day over the course of a year, depth of the tide at a particular location during the course of a day, flickering of a fluorescent light, vibrating of a guitar or piano string. So periodic motion plays a huge part in natural phenomena, and if you take physics, you will analyze this and look at this in much greater depth. Thank you for participating. The end.